Hello and welcome to the Weekly Space Hangout for Wednesday, June 6th, 2018. I'm Fraser Kane, publisher of Universe Today. This week, we're going to be talking about methane dunes on Pluto. New Horizons wakes up, sterile neutrinos detected, and an asteroid is detected and then explodes in the atmosphere. Joining me this week, we've got Dr. Morgan Renberg. Morgan.
Hey Fraser, happy podcast day.
Yeah, Kimberly's not with us today, so we've got to go with say that in her honor. This is for you, Kimberly. We've also got I don't know, someone else, perhaps Dr. Paul Metz-Sutter.
Pick someone. It's me. I'm the only other one.
Who else could it be?
It's always me. Hi, Fraser.
Also, happy podcast day.
If you insist.
I do insist. All right, now before we get into this week's show, I want to give a big special thanks, as always, to the Weekly Space Hangout crew. This is the community that self-formed to deal with the sadness of the fact that we go on hiatus every summer to share news and keep each other's hopes up.
Summer is coming.
Over the day. Summer is coming, and you don't want to be left in the heat when summer happens. So go to wshcrew.space and they will they'll hook you up. They'll give you a place where you can come and hang out in the Slack chat, and you guys can all plan out what guests you want to have in the fall season of the Weekly Space Hangout. So remember, if there are guests that you want to talk to, they will make you an executive producer, and then you get to invite the guests. So go to wshcrew.space and join the community. All right, let's get cranking. Man, this is going to be fun. Paul, I want to start with you.
All right, we're jumping right into
this. So on Monday, it's only been 2 days. You joined me on my live QA, and I ambushed you with the topic of sterile neutrinos. You had no idea.
Yeah, you were like out of nowhere, like surprise neutrinos.
Yeah. Yeah, surprise, the standard model has been extended and Nobel Prizes all around. So
sure.
You've now had 2 days to talk to all the experts, research the literature. Let's talk about the news and your stance on it.
Yeah, I'm not feeling too hot on this news. I want the record to state that Monday I was ambivalent. I was curious. It seemed a little bit off, but I knew that this would raise some tension and some discussion in the community. 2 days have gone by. My reading is there's no serious discussion to be had.
All right. So what's the news?
Neutrino. Yeah. So we want to backtrack. So there's a kind of particle called a neutrino, which is really tiny, barely interacts with matter, only interacts through gravity and through the weak nuclear force. There are trillions upon trillions of them passing through your body right now, but they don't interact, so you don't notice. They are produced in nuclear reactions, in our own nuclear reactors, in the sun. There are 3 kinds of neutrino, called the electron neutrino, the tau neutrino, and the muon neutrino. And there are also antineutrinos, just like everybody else. The big thing about neutrinos, so why there's so much interest in neutrinos as a topic within physics, is they are predicted by the standard model, which is our giant Frankenstein monster apparatus machine for understanding fundamental particles and fields and forces, says that neutrinos ought to have 0 mass. They should be massless, like the photon. Turns out neutrinos do have a tiny bit of mass. How much, we're not exactly sure in some cases. And explaining why neutrinos have mass is something beyond the current standard model of particle physics. So if you can explain that, if you can figure it out with some theoretical model and verify it with experiment, that's like Nobel Prize, because you've pushed the boundary of physics. So that's like the backdrop. And feel free, guys, to cut in anytime, because I don't want to go into straight lecture mode.
Nope. We're entranced.
You are hooked on this neutrino train.
Yeah.
So that's the backdrop. Now, there's a bunch of ideas and theories out there of how neutrinos acquire mass. One of the mechanisms for doing so introduces a brand new neutrino because apparently we don't have enough. A neutrino that is completely and totally chargeless. It does not respond to any forces of nature except for gravity, hence the term sterile neutrino. It's just the most boring particle you could possibly imagine. A ghost among ghosts. And through insert complicated mathematics here, the presence of the sterile neutrino, its existence through various sorts of complicated interactions gives rise to the mass of the other neutrinos. Okay, kind of cool idea, developed a few decades ago. How do you go about looking for a particle that does not interact with any force except for gravity? And this is where another strange quirk of neutrino physics comes in. We're so used to the idea of a particle being a particle that neutrinos are really, really hard to swallow as an object. Like if I were to shoot an electron at you, Fraser, from all the way over here in Columbus, I would shoot my electron gun. The electron would travel across the United States. It would go through immigration and customs. It would enter Canada. It would come into your house and it'd hit you in the forehead. It would be the exact same electron that I sent.
Right.
Right? Right. I mean, it's like no big deal.
Yeah.
If I sent you an electron neutrino, this one particular kind of neutrino, and sent it off to you, by the time it hit you in the forehead, it might be a muon neutrino. It might be a tau neutrino. As neutrinos move around, they cycle through different kinds, through different flavors. They change their identities as they move. And this is very, very strange, but this gives us a potential way to look for sterile neutrinos, because a sterile neutrino would be one of the cycles in the propagation of these neutrinos. So you might have a gun that shoots electron neutrinos, and then as it's traveling to your detector, it will cycle through, like, sometimes it might be a tau neutrino, sometimes it might be a muon neutrino, and sometimes it might be a sterile neutrino.
So you would detect the absence of
bingo.
Right.
Bingo. You would have fewer neutrinos in your detector than you shot out of your neutrino gun.
And then later on, you had the right number again of different varieties. Like at some point, there's going to be some missing number, and that missing number is going to be moving through the whole set. Got it. Yeah.
Exactly. And the job of the theorist is to say, okay, if there is a sterile neutrino, then 1 out of 5 or 1 out of 50 or 1 out of 1,000 of your neutrinos ought to go missing, because that was the time you happened to miss the sterile neutrino. So that's the job of the theorist. Now, people have been looking for sterile neutrinos for decades. And over the past 20 years, there have been some hints of reports of detections of a sterile neutrino, including this most recent result. And in these cases, it's always the same kind of experiment, not the same experiment, but the same generic experimental setup that always seems to find sterile neutrinos. And other kinds of neutrino experiments don't find the same evidence. And this kind of experiment that tends to find sterile neutrinos is a single detector experiment, where you're looking at some neutrino source like a high energy beam or a nuclear reactor or the sun or whatever, and you've got one detector. When you have two detectors separated in space, we find no evidence for sterile neutrinos. two detectors, it's easier to figure out the oscillation because you're measuring the same electron or neutrino beam twice, so you can find any missing neutrinos really easily. Single detectors, it's possible, but it requires a much clearer understanding of the fundamental physics that are happening inside of your detector apparatus that I'm not going to get into details of because I don't fully understand it.
Yep.
Because this immediately goes into the weeds.
Yeah.
And so when this result comes out, like, oh, we have a 4.1 sigma detection of sterile neutrinos, that's assuming that they perfectly understand the fundamental nuclear interactions happening inside of their detector, which are ferociously complicated. The detector itself is a complicated beast.
And I think it's really important to kind of set the stage here in that we're talking about this. This is news because should the sterile neutrino be found, it is an extension to the standard model. It is the first piece of particle physics that's ever been found that extends beyond the standard model. I mean, the Large Hadron Collider has been colliding as hard as it can, and it has still failed to turn out any particles that are outside the standard model. It is boringly filled in lots and lots of pieces, but at the end of the day, it hasn't been able to find anything to offer any new physics. So to find something like this sterile neutrino, we are well into Nobel Prize territory. And
this is like identifying dark matter. This is huge.
Yeah, and so then it opens up. It tells physicists what direction to move for all the further theories to extend the standard model to understand what else is going on out there. And that's why it's so important to sort of be extra skeptical. It's that same sort of state that we had when Bicep 2 turned up those primordial gravitational waves. Amazing if it's true, but anything, that looks, so what did Sagan say? Extraordinary claims require extraordinary evidence. And this is in that thing.
So why do you think, so let me rephrase. Knowing nothing about neutrinos or the physics, the fact that we've been searching for these things for 3 decades, and now we're publishing a result that's like 4 sigma, on its face doesn't seem very good. 4 sigma doesn't really cut it in physics. And if you run experiments consistently for 30 years, you're going to get a 4 sigma result. So I'm sort of surprised that just on the face of it, that is anywhere near good enough to even sort of entertain this as the definitive word on something this important.
Well, that's an excellent point. And in my understanding is within the neutrino community, the particle physics community, it's not. This is not a very interesting paper.
Right. Because, the response to the Bicep 2 announcement with the primordial gravitational waves was to go back to the drawing board and say, okay, fine, there could have been dust in the way, so let's aim 5 different instruments that are going to search many different wavelengths to unambiguously know if we're dealing with what we think that we're actually detecting, what we think that we're looking at.
I have some background information on Bicep from those heady days. In order for Bicep to properly interpret their measurement from the early universe, like you said, there's a bunch of dust in the way that can screw up their signal. So they needed to model the dust. They need to be able to subtract out, like, okay, here's the dust. We're going to subtract that out of the data. And then what's left is the juicy cosmological signal. At the time, I was actually a member of the Planck collaboration, which was measuring the cosmic microwave background across the whole sky and also producing dust maps. And some of the Planck collaboration gave a talk at a conference where they showed some preliminary results of our dust maps and our dust models. Someone from the Bicep collaboration took a picture of it and use that picture of a slide from a conference talk to build their dust model, which they used to claim their result. When that came out internally in Planck, we said, we looked around and said, one, who released that information, because it's supposed to be embargoed, and two, they're wrong. Like, we know, because we had updated our dust models since that conference, and we knew that the bicep result was wrong as soon as it came out. But we had to take our time to say why, because our own results hadn't been made public yet.
So, but with the same sort of strategy with bicep, like as I said, there are many more, far more elaborate surveys in the works now across many different instruments. There's one down in Antarctica. There's some in Chile. Mm-hmm. There's space-based ones. They're looking at a different wavelengths, and they're going to try to know once and for all if this is the case. Yeah. Is this the beginning of a new sort of way to look into this question, or is it just like, do you think it's going to dead end at this point, or do you think people are going to go deeper?
So neutrinos themselves are absolutely fascinating because we don't understand why they have mass. And there's a lot of theoretical and experimental efforts to hunt down more neutrino properties. This idea of a sterile neutrino, I get the impression that it had its chance already. And this is like but there's still a few groups that are just hanging on, desperate to push it through, because if they win, the grand prize is a free trip to Stockholm and
a couple of $1 million.
And so there's also that, because there's a high risk but high reward kind of scenario to keep them incentivized, which is good overall for science. We need people to keep pushing even on unpopular ideas because it might pan out. But sterile neutrinos as a model just don't work, because if you introduce sterile neutrinos with the properties you need to explain this result, you mess up other observations. You mess up what we know about the early universe. You mess up what we know about the total amount of stuff in the universe, the matter content of the universe. There are other ways, roundabout ways, to constrain neutrino properties, and those already rule out a sterile neutrino. So if you introduce a sterile neutrino, you have to add even more new physics to explain away all the other results. And so you're at like the double new physics level, right, which is double cool, but also double challenging.
Well, but if you do, then that's other physics problem, not yours. Right? If you can find it and be certain that it's there, then the messing up of other people's physics is really not your concern.
It's not your concern until you show up at a conference and start presenting your results, and then they raise their hand and they say, what about omega matter?
Sure.
What about the clustering? Yeah. What about the cosmic microwave background fluctuations?
Yeah, and you just say, I don't know. Yeah, you say, here's this really incontrovertible evidence that I've found that this particle exists, so this is not my problem. This is your problem with your omega.
Nowadays that approach probably won't get you very far. You're welcome to try, but people are gonna say, no, I've measured the cosmic microwave background really, really, really well, and it says you're wrong.
Oh, fine. All right, Morgan. Incontrovertible evidence that there are sand dunes on methane, made of methane.
4 sigma sand dunes.
4 sigma sand dunes.
I think that sand dunes are some of the most underappreciated things in geology and planetary science, because we see them all over the place, and yet they only can form under certain ranges of conditions. So they're one of these really neat observations that you can make that, without knowing anything else, suddenly collapses down the number of possible combinations of a variety of parameters to a much smaller number. And so a paper came out this week pointing to some formations on the edges of the heart of Pluto, kind of where the big icy nitrogen plain meets the water ice mountains, and suggesting that some of those bear quite a resemblance to dune-like structures that we see elsewhere in the solar system. And we see dunes on Earth, of course, we see dunes on Mars, there's good evidence for dunes on Titan, but dunes can only form when certain things happen. You need wind speeds to be a certain amount relative to the size of particles. You need the shape of those particles to be a certain size shape relative to their size. You have to take into account the gravity of the body that you're on. You have to take into account sort of the stickiness of the particles, which ties in with the temperature and even the pressure of that area. And so what these researchers did was take this purported dune structure and say, okay, if this is in fact a dune, what does that tell us about the surface properties in that area? And so it's a very sort of simulation theory-based approach, but it provides some interesting insights. And so what they did is they looked and said, okay, well, given we know some things for sure, we know the temperature on Pluto for sure, we know the surface gravity on Pluto for sure. Given the shape of the mountains and the thickness of the atmosphere, we can probably estimate the wind speed coming off of those mountains down, sort of flowing down onto the plain, just like wind comes up over the Rocky Mountains and flows down onto the
Pluto. I need to know this number right now.
I actually have no idea what the actual number is.
What the wind speed is?
Yeah, I want to know that.
Well, so I'm just looking at the article. The atmosphere is 100,000 times thinner than our atmosphere.
Yeah, I still want to know how fast that one particle of nitrogen moves. I just want to know.
Yeah.
One molecule.
Wow. So what they sort of concluded here is that the most likely scenario, if these are dunes, is that the sort of sand particles making up the dunes are made of methane. It was either going to be methane or nitrogen. And given the sort of hardness necessary to form the dunes, they said methane makes more sense. And the particle size would actually be very similar to the particle size that we see in sand dunes here on Earth, which is something like 0.2 or 0.3 millimeters. But then they kind of encountered a problem because they realized that with those constraints, the wind on Pluto would do enough of a job piling up the sand, but the wind probably isn't strong enough because it's so thin to actually get the particles moving in the first place. So once you got the particles moving, the wind was sufficient to pile them up as they appear on the surface, but they couldn't get the wind started in the first place. And their solution played off of something that is really, really unique to Pluto, which is that it goes through these pretty substantial changes in surface temperature. So the surface of Pluto is something like 40 Kelvin. But because Pluto's orbit is pretty elongated, that value can change by several degrees over time. So 3 or 4 Kelvin, which might not seem like a lot, but that's a 10% change in the absolute temperature of the surface. And that actually causes the elements on the surface to sublimate and deposit in these cycles. And that sublimation deposition cycle is what probably causes things like that weird dark spot on Charon. And so what their simulation showed is a few degree warming of the surface would cause sublimation. And the air molecules or the nitrogen molecules sublimating off of the surface would be enough to jar loose these methane grains that then the wind could pick them up. Wow. So basically, as the surface sublimates underneath them, it filters up and carries up the dust with it, and then the wind moves it along. And this is a kind of mechanism that essentially could only happen on Pluto, where your gravity is so small, your atmosphere is so thin, your temperature changes are relatively large relative to your working medium. So if we could get down there and see these dunes, they might actually look a lot like Earth dunes, but their formation mechanism would almost be completely different.
That's fascinating. I mean, they found dunes on Titan. There's obviously dunes on Mars. You see dunes at the bottom of the ocean. Like all of these different situations where dunes can form, and to have this structure on Pluto is just mind bending.
Is Pluto the exception here when it comes to mechanism of dune formation, or does each planet gets its own its own dune story?
Would you expect to see them on Triton and Sedna?
Yeah.
So that's a good question. I'll answer Paul's question first, which is, to my understanding, and I'm not a planetary geologist, the dunes on Mars have generally the same mechanism as the dunes on Earth. Their ultimate shape is a little bit different because the gravity is different, the atmospheric pressure is different, so on and so forth. But the general idea that wind picks up the particles and kind of bounces them around in these sort of half circles along the surface, and that's what yields the distinctive dune pattern, is basically the same. And I think you would expect to find dunes basically anywhere you have an atmosphere, because without an atmosphere, you have nothing to pick the dune particles up. Then at that point, you basically just have piles. And there's probably plenty of places in the solar system that have piles without having dunes. To my knowledge, we don't know much about a substantial atmosphere, say on Triton. By substantial, I mean even by Pluto's standards, substantial. Nor do we know much about a substantial atmosphere on Sedna. So if the conditions were right, that there could be an atmosphere there, then probably there is some activity or evidence for dunes, so long as the wind speed can be enough. So if you, like, Triton is kind of weirdly perfectly spherical, which might mean that there's not, with those changes in topology that we see on Pluto, is what generates the wind speed fast enough to pick up the particles or move the particles once they're picked up. If you didn't have that wind speed, like you might not on Triton, even the presence of an atmosphere might not be enough.
Right.
But we really have no concrete evidence.
Wow. All right, moving on. So my turn, and I'm going to talk about an asteroid. So on Saturday, almost a week ago, I guess 5 days ago, astronomers at the Catalina Sky Survey, I'll bring up my story here, detected a fast-moving object out beyond the orbit of the moon. And it was sort of a streak, and so they knew that it was on its way to actually crash into the Earth. And this was the third time that astronomers had ever detected an asteroid before it crashed into the Earth. Now, they sort of pretty quickly realized that the size of this object was just a couple of meters across, and they calculated the impact trajectory, where they thought it was likely to sort of strike the Earth, from sort of Africa across the Indian Ocean and into Southeast Asia. And then right on schedule, folks in Botswana, and this is sort of this video that I was showing here, folks in Botswana saw a really bright meteor in the sky, a big fireball. There we go. So I'm going to show it. Really, really bright. And this was someone just caught it on a cell phone camera looks like it was over a mountain, so we don't have a really good view of it, or that I've seen anyway. And, you know, as asteroids go, these things hit the Earth all the time. But when you think about what's really sort of exciting and interesting about this is that the folks at the Catalina Sky Survey used this sort of alert system to send out an announcement of the space rock. It went to NASA's Minor Planet Center. It went to the Center for, I forget the name of it. What is it? The Center for Near Earth Object Studies. And they did their analysis of it and then decided that it wasn't dangerous. And what's great about this is the system works. You've got a detection of an object that's on its way to hit Earth, and the right people are notified and are able to analyze it and send out, theoretically, a warning. And the last time that we had an object that wasn't detected but caused a problem was, of course, the Chelyabinsk impact back in 2013. That was an object that released, say, 400 to 500 kilotons of energy, and more than 1,000 people were sent to hospital with injuries, from glass shattering as the airburst went off in the sky. So you can imagine, the problem with the Chelyabinsk impact was that the asteroid actually came right from really close to the sort of the radiant of the sun, and so it was obscured from the sky, and people weren't able to know that it was coming. But imagine if this object was coming in from more like an orbit of what this object that hit on Saturday did. You would have had several hours of warning. You could have sent out an alert to everybody to say, if you see a bright flash in the sky, don't go near your window. People were blinded temporarily because of what happened with the Chelyabinsk. So to have this system work, I think is pretty exciting. And fortunately, it was just 2 meters across.
So is there like a red phone that they can pick up and call the president and say, issue the alert?
Yeah, issue
the alert.
I mean,
it seems like
there's a blinder.
Even if you could know 3 hours in advance, how would you get the word out?
Well, and I
fast
think
enough.
The thing here is that this is how you get Triffids, right? When you think about the day of the Triffids, there was this weird meteor shower, and everybody went out and gawked at it, and they all got blinded, and then carnivorous plants rose up, and everybody was blind. So I think that really is the purpose of this research is to prevent against Triffids. So now, of course. Oh, go ahead.
I was just sarcastically agreeing with you.
But I think so. That is sort of the. I mean, I love the fact that this system works, and it also just shows you sort of that these objects are out there. Of course, astronomers only know of a fraction of the 140 meter sized asteroids that are in our near Earth environment. I think they know they've detected 8,000 that are 140 meters across, and they think that's probably about a third of the ones that are in our region. And so to build a better series of instruments, one of the ideas was this idea of the NeoCam, where you place a telescope out in, say, the L1 Lagrange point that has a view that is different from the view that we have here on Earth. And so it can detect those asteroids kind of as they've passed it to know that one is coming our way. And with more hours of warning, days of warning, you can take some more serious precautions. It's kind of like a tsunami warning, I guess. So the system works. I would have loved to have seen the fireball. Have you guys ever seen a fireball?
No, I've never.
Yeah, I've seen one, and where significantly brightened the landscape, and that was pretty amazing. Like, you're out watching meteors, and then one just comes through. Everything sort of turns almost not like day, but really well illuminated. And the one that I saw actually kind of broke up into pieces as it was going through the sky.
That's so cool.
Yeah, it was amazing. So that's what I got. Morgan, you had one more story you're going to bring up.
Yeah, I just wanted to mention that yesterday, New Horizons received the command to wake up from its hibernation, and it did it. And its instruments are all working as intended. And so it's now about 6 months out from its flyby of Ultima. Is it Thule? Thule? We were debating this before. And Thule?
Yeah. Thule?
A really cool Kuiper Belt object, which will take place, depending on where you live, about New Year's Day 2019. So we're about 6 months out from that. And they had to wake it up so early because it's so far away. It takes forever for anything to happen. So one of the most important things left to do is to upload the final sequence of commands that will sort of define where the cameras are looking and the instruments are pointing at every moment along the path. And they've prepared 2 potential flybys. that they'll be able to sort of switch between at the last second. But to upload those two flybys will take the next 2 months because it's receiving data at, like less than a kilobit a second. And some instruments have come on periodically during hibernation and made observations, things like the interstellar particles or interplanetary particles between Pluto and this Kuiper Belt object. And they need to download that data off the system so they can basically clear space. It's like all of us trying to install that system upgrade on our phone, and you have to delete a bunch of apps in order to actually make it happen. That's basically what they have to do. But downloading that data is going to take more months.
You have to have to wait a day for every request that you send to the spacecraft for it to acknowledge it and send back its acceptance of the request.
Yeah, so 6 months is enough time to sort of give ourselves a safety margin, but it's not like crazy early given the magnitude of what's left to transfer and the time that it's going to take to do that. But we're in the final piece now of the New Horizons mission. I remember thinking in 2015, it was July 2015 when it flew by Pluto, thinking, oh my goodness, January 2019 is so long away. And suddenly here we are, and we're right on the doorstep, and it's going to fly by up to 3 times closer to this much, much smaller object than it flew by Pluto. And so fingers crossed, we should get some amazing images just like we did of Pluto, and who knows, maybe we'll find some dunes.
So just one quick callback here. John Yogerst is saying that on BBC, they said 10 meters per second for wind speed.
I saw that.
Yeah.
That's great.
Wonderful.
22 miles an hour. Which is great. So that's a nice, pleasant breeze if you can feel it.
At 100,000th the air pressure of Earth.
While you were talking, I did some very, very important research. And according to dictionary.com, the original Latin pronunciation of this target is Ultima Thule. But the more common pronunciation is Ultima Thule.
Ultima Thule. All right. Well, you learn something every show.
Because it was first recorded in 1655.
All right.
The Latin?
Well, Latin was the language of science at that point.
Yeah. Oh, I see. Like the last time it was recorded by people.
Yeah, I don't think that was the sound recording.
Yeah.
No. There's a bigger breakthrough there if that's the case.
Yeah.
Of human languages.
All right, let's move on to our interview. Interview's over. Don't worry.
One yet.
The interview's going to happen at the end of the show. It's pre-recorded. All right, well, it's time to wrap things up. So I'm going to give people a chance to shamelessly self-promote things. Morgan, what are you working on?
Yeah, well, I will not be on the show next week because I'll be out in sunny Pasadena for the AstroViz Astronomy Visualization Conference. And I'm going basically to remind everybody there not to take themselves too seriously. This is going to be a conference of like supercomputer simulations of various things in space. And I'm going to give my talk about a clip we did in our most recent planetarium show in which we floated elephants into the Earth's atmosphere in order to create a metaphor for the amount of carbon dioxide that we're polluting into the atmosphere. And it's basically as far from a serious astronomy visualization as you can get. But I'll argue that it more effectively gets across the message that we wanted people to take home than a billion compute hours on some sort of neutron star.
That's awesome. Paul?
Let me see. I think I'll plug my blog again, where I talk about issues like what's going on with this neutrino result. How can we properly interpret that? How can we build a properly skeptical attitude without being too skeptical, overly skeptical of science? Because, we do want you to trust science and scientists, but it's also a very human and messy and complicated endeavor. So I talk about these kinds of issues of how scientists should approach science communication. But it's a free-for-all blog, lots of discussion points, very, very short pieces, less than 500 words a week. So very quick reading. It's pmsutter.com/notes. The name of the blog is Ab Initio.
All right.
Yeah, I want to endorse Paul's blog specifically for its brevity. There's only so many hours in the day to read Atlantic length blog posts. And so if you really just want a few paragraphs that get the point across, then Paul's blog is the way to do it.
Awesome. All right, and so we're just about to release our next episode on the Guide to Space. It's going to be all about space power, the different methods of power from space, and which ones are the good ones, which ones are the ones we're working on right now. And then the episode that I'm working on next is going to be a lot of fun, and it's all about the 4 astrophysics missions that are outlined for the decadal survey for coming up.
The 4 horsemen of the apocalypse.
Yes. Yeah, and so on the one hand, you just get so excited about these observatories. LUVOIR is the one everyone's probably heard of, but there's HabEx, which is going to be directly observing habitable worlds around other stars. The LYNX, which is like a super duper Chandra, and then the OST, which I haven't got to yet. So it's
I really hope that stands for old school telescope. And it's just like a dude on a mountain with a mirror.
They're all monsters, and the thing that's really kind of sad is that they're all told to go just like, think out of the box, let your imaginations run wild. And now is the part where they're like, James Webb is going a little over budget. WFIRST is going a little over budget. Maybe you should just rein it back in a little bit. And so now they're starting to target, like maybe they've only got $3 billion to build their spacecraft, when before they were potentially $5 billion and up. And the LUVOIR, could be an 18-meter telescope, as a successor to the Hubble Space Telescope, right? The optical, infrared, but that is maybe getting its budget brought down because it's easily a $20 billion telescope. And that one is the one that the budget's going to go a lot higher. But, just imagine what it could end up being. So can you imagine the cost overruns on a 20 billion estimate? It's 100 billion. It'd be like
or the time overruns,
the schedule overruns. Yeah.
Even be alive when it has first light.
Yeah.
Maybe me and Morty.
Yeah, like in the mid 2030s probably is when they're looking at maybe being able to see it actually launch. But you would know better than me. You've got some friends.
Don't hold your breath.
Yeah. But I really want this telescope. Actually, the HabEx one I think is the one that feels most practically exciting to me. So anyway, that'll be next week. All right. So let's say thanks to everybody. Thanks, of course, to the people watching the show live. Thanks to the WSH crew. You've only got 3 more episodes after this. Three more episodes after this, and then we go on our summer break. So join the WSH crew. Let them help you through the hard times over the summer so that we can then return in the fall. And thanks, of course, to my co-hosts. We'll see you all next week.
Bye.